Hello, followers of Neuro Takeaway. This week, we are going to analyze a very funny pattern of enhancement. What do these images have in common? Well, they are all MR images on T1 with gadolinium, and they have areas of enhancement with a linear and punctate pattern. Some of them are isolated, others are multiple. Some of them are surrounded by normal parenchyma, others by hypointense areas of parenchyma, and others by areas of homogeneous enhancement. But what does this mean? Okay, in general, for us, this means perivascular enhancement. And here you have several diagnoses. Here from left to right in the upper row, we have an HLH, hemophagocytic lymphohistiocytosis with macrophagic activation, then a tumefactive plaque of a demyelinating disease, then a pattern of encephalitis by anti-GFAP antibodies, glial neurofibrillary acidic protein, and finally a CLIPPERS. CLIPPERS stands for chronic lymphocytic inflammation with Pons perivascular enhancement responsive to steroids. At the lower left corner, you have a primary CNS lymphoma, and on the right side, we have an autoimmune lymphoproliferative syndrome. But do we really know what we mean when we say perivascular space? Is that the space at the periarterial, perivenous, or pericapillary level? Well, to understand this point, we have to look closer at the microcirculation of the brain. When an arteriole runs through the subarachnoid space and decides to penetrate the parenchyma, it's accompanied by a double layer of pia mater, one from the periarterial zone and the other from the parenchyma zone. This double layer of pia goes through a certain distance and then disappeared, forming a funnel-shaped compartment, which is called the arterial perivascular space. This space contains CSF, and if we do a cross-section at this level, we will find the following layers. From the inner side to the outer side, we first have the endothelium with its basement membrane, and in this membrane you can find the pericytes, then the smooth cells layers, then the pia mater with its own basement membrane, the first layer of the pia mater, then the perivascular space. After that, you have the other layer of pia mater with its basement membrane, and then the parenchyma. The encephalic parenchyma at this level is represented by the glia limitans, which is a layer of the formed by the feet of the astrocytes and its own basement membrane. So it's a pretty complex picture. But what happens further on? At the capillary level, we don't have the pia mater, so there is no perivascular space, and there is a fusion of the basement membranes of the endothelium and the glia limitans. After that, we have the venous, and this level is very important for us. Here, these two basement membranes separate again, forming another perivascular space, which is called the perivenular perivascular space. At this level, we find CSF and some cells as macrophages and antigen-presenting cells. And it's precisely at this level where gadolinium accumulates when we have perivascular enhancement. So now that we know where is our perivascular enhancement, we have to understand the different patterns that we saw at the beginning of the talk. And to understand this, we have to know the venous anatomy. Here we have a very nice cartoon of the venous microcirculation. You can see here the deep and superficial medullary veins, and some of them are transcerebral. So if we make a slice at the cross-section of these vessels, we will find a punctate or sand-like pattern. If we perform a slice along the longitudinal axis, we will find a striated pattern. But anyways, what we are seeing is gadolinium at this specific compartment, and we have to understand that this is not the target of the inflammation. This is just a gateway through which certain cells and substances as chemokines and cytokines get access to the brain. This is like the first battle of the inflammatory war. Okay, but what is happening here? To understand this, we have to know the importance of the microcirculation in the brain. To have an idea, it occupies around 12 square meters and 160 kilometers in length. It represents around 30% of the brain volume. But this is not a mere physical barrier. It is a more complex structure. There are many cells, the endothelial cells, the microglia, the astrocytes, the pericytes, and the neurons themselves that are in constant crosstalk, including there is a crosstalk among the endothelial cells and the flowing cells as lymphocytes and macrophages. And this is what is known as the neurovascular unit. And this neurovascular unit has two states, let's say two flavors. One is the normal, the resting state, where it is relatively impermeable to many substances and cells, trying to keep the brain microenvironment very stable to allow the very important process of neural conduction. But there is also an inflammatory state, and we don't really know yet which is the first trigger of this change, but there are many possible mechanisms that can be going on at the same time. For example, to start with the physical mechanism, after stroke or after brain injury, this brain can be disrupted and be more leaky. On the other hand, there are some antibodies, flowing antibodies, that can attach to certain endothelial cells receptors, triggering some changes, some production of some chemokines and cytokines. On the other hand, there is an increase in some transport proteins, allowing the transcellular transportation of inflammatory products. And at the same time, there is a downregulation of the proteins that formed the tight junctions, allowing the paracellular transportation of these cells. Regarding the blood, there is an increase in some adhesion proteins as VCAMs that are of crucial importance to call, let's say, or to allow the attachment of the flowing cells, the lymphocytes, to the endothelial cells. And finally, there is a very favorable microenvironment in the brain with this state to the aggregation of B cells, forming niches that can produce antibodies inside the brain. That is what we know as for example, the oligoclonal bands that are found in some processes as MS in the CSF. So in reality, we don't know, but there is a combination of some or all of these mechanisms that produce this inflammatory state. Okay, just to finish up, I would like to remind you the classification of vasculitis of Chapel Hill of 2012, where the focus was placed on the type of vessels involved. We have the arteries, large and small arteries, capillaries, venules, and veins. But today we talked about the perivascular pattern of enhancement, which is perivenular pattern in reality, and this is not a real vasculitis because the target is not the vessel. This is just a first stage of an inflammation process where the target is beyond the vessels. So I hope I was clear enough, and let's see you next week. Bye-bye.